Hello everyone. Today we discuss properly divergent sequences. In previous session, we studied several techniques and theorems about convergent sequences. Today we switch gear a little bit and focus on not convergent sequences, namely properly divergent sequences. So basically, we will explain the meaning of a sequence converging to plus or minus infinity. Recall that plus or minus infinity are not numbers. They do not belong to the set of real numbers. They are just symbols to convey certain meaning. Now, here is the definition. We say that the limit of a sequence xn is equal to plus infinity if for every alpha in the set of real numbers there exists a number k, a natural number k, such that for any index n bigger than equal to k, then xn must be bigger than alpha. Here, the way to think about this definition is follow. You pick a very big number alpha, then it says that there must be, even though this number alpha is very big, there must be some natural integer k, such that for all index bigger than k, then any element xn must be bigger than alpha. It It is true regardless of how big the original alpha is chosen. What it means is that the sequence keep increasing towards infinity eventually. In other words, this is also behavior at infinity. Similarly, a sequence is said to converge to minus infinity if the limit of minus Hn is equal to infinity. And a sequence is called properly divergent if the limit is equal plus or minus infinity. So properly divergent means it's not conversion. And furthermore, we know exactly what direction it is diverging to. It is diversion either towards plus infinity or towards minus infinity. This is to distinguish from just zero divergence, because for zero divergence, you might arrive at a situation where a sequence only assumes certain values, let's say 1 and minus 1, and the sequence is not convergent, but it also not properly diverging towards plus or minus infinity. Now here is an example. Let's consider the sequence xn equal to n. We want to show that the limit of xn here equal to plus infinity. Here is the proof. Pick any number alpha in the set of real numbers, and we choose k depending on alpha to be the first integer such that k of alpha is greater than alpha. And this is possible because of the Archimedean property. Remember, we discussed the completeness property, which implies the Archimedean property, and then the Archimedean property further leads to several consequences about the density of rational and irrational numbers. One of the consequences that for any number epsilon, for any number alpha in the set of real numbers, we can always find integers bigger than alpha. Then for any index n bigger than k, then certainly Hn equal to n bigger than k bigger than alpha. The definition for properly divergent sequence is validated, is verified, and that's why the limit of Hn here equal to plus infinity. Here is another example. C for some number c greater than 1, Hn here equal to c to the n. We would like to show that the limit of Hn is also equal to plus infinity. So the proof here follows from a very similar pattern to the previous example. However, the new content, the new element here is that the algebraic inequality gonna come from a well-known inequality called the Bernoulli inequality. So this is one of the inequalities that is mentioned at the end of chapter 1. They're gonna allow us to compare the power number. So in general, the Bernoulli inequality says that 1 plus x to the n is greater than or equal to 1 plus x n x for any uh, positive number x. And using the Bernoulli inequality, we would be able to choose the number k depending on f on alpha accordingly. Now, the next theorem is that a monotone sequence is probably divergent even only if it is unbounded. And this is not surprising because we have a previous statement which says the following. A monotone sequence is convergent even only if it is bounded. So the negation of that statement is exactly the statement we see here. If the sequence is unbounded, then it is divergent. Furthermore, because it is monotone, so we know that it must diverge either towards plus infinity or minus infinity. Another statement is about a comparison result. Let's consider two sequences xn and yn, and furthermore assume that xn is smaller than or equal to yn for all natural integer n. If the limit of the smaller sequence is plus infinity, then intuitively the limit of the bigger sequence yn is also plus infinity. On the other hand, if the limit of the bigger sequence yn is minus infinity, then the limit of the smaller sequence is also equal to minus infinity. We also have a ratio test. Let x and n and yn be two sequences with xn and yn are all positive numbers. Assume that the limit of xn divided by yn equal to L, which is bigger than 0. Then the limit of xn equal to plus infinity, even only the limit of yn is also equal to plus infinity. Why? Because in this case, the ratio xn divided by yn eventually settling down to some number L bigger than 0. That is, eventually xn and yn are proportional to each other. That's why if one sequence is diverging towards plus infinity, then the other sequence, which is proportional to the previous sequence, must be diverged, must be divergent towards infinity as well. Now here is an example how we can use the previous the established theorems to study certain sequences. So let's consider the sequence xn equal to the square root of n squared plus 1. Now, in order to understand this sequence, imagine n to be a very, very big number. Then n squared going to be a very, very big number. That's why n squared plus 1 will be very, very close to n squared. In other words, n squared is the dominating term in comparison with 1. That's why when n is big, we have the approximation that the square root of n squared plus 1 is approximated by the square root of n squared, which equal to n. And that allows us to use the previous theorem. So we consider two sequences, xn equal to the square root of n squared plus 1 and yn equal to n. And we consider the ratio of xn divided by yn and take in limit. The limit here going to be equal to the square root of n squared plus 1 divided by n, which by algebraic manipulation equal to the square root of 1 plus 1 over n squared. Now, applying the compatibility theorem we established in the previous section, we can interchange the limit operation with the square root operation and also the addition operation. That's why the limit of the square root of 1 plus 1 square, 1 over n square equal to the square root of the limit of 1 plus the limit of 1 over n square when n approaching infinity, which equal to 1 plus 0, which equal to 1. So in this case, the ratio is approaching 1. That is, these two sequences are proportional to each other, are eventually close to each other. Since the sequence yn equal n is properly divergent towards infinity, according to the previous example, the other sequence xn must diverge towards properly diverge towards plus infinity as well by the comparison theorem or the ratio test that we mentioned earlier.